All right, so maybe we will now resume our lecture material. And there's now a drastic shift. We no longer talk about network analysis, but rather about prediction methods. And oftentimes, networks are used in what I would call unsupervised machine learning method approaches. For example, to find modules. And remember, modules are found using a clustering procedure. And this is a technique known from unsupervised learning. Also, networks are often used to find biologically important genes. And so one would refer this as a variable selection approach. But now I will turn to a third type of machine learning analysis, which is really to predict an outcome. For example, we would like to have a blood measurement and predict onset of disease 10 years later. And in my opinion, machine learning approaches are really better suited for making these types of predictions. At least I have not yet been entirely convinced that network-based approaches are better at predicting outcomes than these standard tools. And so I will now talk about a new prediction method and compare it to alternative procedures. And it will be interesting to you because it involves a lot of empirical comparisons, and I think you will appreciate that. So just to remind you, there is a technique in biostatistics called generalized linear models. So these are flexible generalizations of ordinary linear regression. For example, you may have heard of logistic regression, right, if you have a binary outcome, or Poisson regression if you have a count outcome. But there's really a vast class of generalized linear models. Now, another outcome I mentioned is censored survival time, and that is not modeled using a generalized linear model. It's often modeled using a Cox model. But I just tell you right away that our software allows you to also predict censored outcomes. So in any event, so this is this little footnote. Random GLM, the software I will describe shortly, can also apply to survival outcomes. Now, there are well-known common prediction algorithms. For one thing, just plain old generalized linear models. For example, logistic regression is very popular, and the truth is it works really well at predicting binary outcomes. There are much more sophisticated approaches based on penalized regression models. For example, elastic net and lasso. These are very popular approaches in genomic applications. Then you may have heard of so-called tree predictors, classification trees, and RPART, and so on. And other techniques are linear discriminant analysis. That's an age-old method. K-nearest neighbor predictors, support vector machines, shrunken centroid methods by Tip-Shirani et al. And finally, I come to so-called ensemble predictors. So what are those? These are collections or ensembles of individual predictors. For example, when you have one tree predictor and you can start with that, but you create various tree predictors and you get an ensemble of trees, and then this can often greatly increase the accuracy. So a special case of such an ensemble predictor is, of course, the random forest predictor, which is well known and a state-of-the-art method developed by Leo Brayman. So one way to obtain an ensemble predictor is by a technique called bootstrap aggregation, also known as bagging. And so how does that work? So let's say you have one data set, 100 people, 50 diseased individuals, 50 controls. And what you do is you fit one prediction method, and there's your one predictor. But what you would like to get is you would like to get additional data sets. So one way to do it is by this non-parametric bootstrap method, which is to randomly select subjects from this original data set with replacement. So you start with your 100 subjects, you randomly select people from that data set with replacement, and so in the new data set, you roughly have 63% of the original subjects, but some of them have been sampled repeatedly, right? And then what you do is you fit a predictor on this new data set, the bootstrap data set, and there it is. There's another prediction method. And so you can repeat this bootstrap method several times, and you can get hundreds of predictors. And when you have then 100 predictors or 500 predictors, you can let them vote on your prediction. And so you aggregate their votes using, for example, plurality voting. And this method was introduced by Leo Brayman in 1996, and it worked very well. Now, at a later point, I want to say 5 years later, Leo Brayman published a variant and improvement of that method, which is known as the random forest predictor. And the random forest is a collection of individual tree predictors. Now, the random forest is so well known because it has a phenomenal predictive accuracy. It's a state-of-the-art method. Its main advantage is the high accuracy, but this comes at a cost, which is, in general, ensemble predictors are hard to interpret, right? Because you have, for example, 500 trees, and it's very hard to understand what it means. Now let's look at another statistical approach, which is just forward regression model, right? So let's say you have a logistic regression model that you fit to your data, and you could do something called variable selection based on forward variables selection techniques, which select variables based on an AIC criterion, for example. This is a technique that is well liked by medical doctors and epidemiologists. Why? Because they start with 20 variables, they apply variable selection, they end up with 3 variables, and they like it because they arrive at a model that is very easily interpreted. It will say smoking is bad for you and being a female is good for you. Nice interpretation, But this variable selection step has one major drawback, which is it really compromises the predictive accuracy. Why? Because you overfit the data. It looks at the variables that seem to fit best, and by doing it, it overfits. So the rationale behind the random generalized linear model predictor is to combine the advantages from both of these approaches, meaning the high accuracy of the random forest predictor, but also getting the easy interpretability from a forward selected method. So let me review or describe the random GLM construction. So the random GLM is an ensemble predictor based on bootstrap aggregating these generalized linear models, but there are certain tweaks to the construction. For example, it makes use of forward variable selection, okay? And so just to highlight that, let's look here at a description of 2 seemingly bad choices. So let's say you start with a logistic regression model. Then, as I mentioned to you, actually it has very good accuracy. However, if you decide to apply forward regression to the variables, in other words, you go up on the y-axis and you say, yes, I apply forward variable selection to that, that's a bad choice because you overfit the data. The accuracy goes down. On the other hand, let's say you have your logistic regression model and you decide I will bag it by bootstrap aggregation. Then, so in other words, you walk along the x-axis and say, yes, I bag the predictor. Then it turns out that this is not a good idea. Why? Because one can show that bagging a logistic regression model actually doesn't improve the accuracy, but it greatly makes things complicated. Instead of one logistic regression model, now you have 500. And so you there's no chance you can interpret it, you know. In any event, the random GLM actually makes two wrong choices at the same time. It applies variable selection and it applies bagging to it. And it does a few other things, but by making these two wrongs make a right, because I hope to show you that the resulting predictor is actually extremely accurate. So to go through the details of the random GLM construction, so let's say you start with one big data set, let's say 100 subjects and 20,000 genes. How would we proceed? So in step number 1, we do this bootstrapping. We apply the bootstrapping approach to generate, let's say, 500 bootstrap data sets. All right. Now, in step number 3, what we do is we carry out what is known as a random subspace selection. And so what does that mean? So remember, you have your 20,000 genes in each data set, and you randomly select, I want to say, 5,000 of these genes, randomly. And you do that for each data set. You randomly select some genes. Now, optionally, you could construct pairwise interaction terms between these genes, these 5,000 genes. However, when you have a high-dimensional data set, for example, gene expression data or methylation data, we don't recommend that you introduce interactions. So in any event, you have your 5,000 randomly selected genes, and now what you do is you rank order these 5,000 genes using what we call standard variable selection, just based on correlations, for example, or a differential expression. And let's say you take the 50 genes that have the strongest relationship to your disease outcome. So, right, so see the flow. You started with 20,000, 5,000 randomly selected, 50, out of those then 50 genes with the strongest t-test, for example, with the outcome. And now you take these 50 variables and apply forward variable selection. For example, using a logistic regression model. So then what will happen? You will end up with a logistic regression model that may contain 3 or 4 variables out of these 50. Okay? And so now you have down here all these different logistic regression models, let's say 500 logistic regression models, and each of these models allows you to estimate the probability of having the disease, and then you aggregate these probabilities in an intelligent fashion to arrive at a final estimate of the disease probability, in other words, at the prediction. Now, let's evaluate this approach. So as I mentioned, we carried out very comprehensive empirical studies of various prediction methods. And it turns out that in all of these comparisons, the random GLM ranked very highly. So in a second, I will describe to you an application to 20 disease-related expression data sets, mainly cancer, but other diseases as well. Then I will describe another study where we evaluated 700 data sets, then UCLA benchmark data and simulations, and that's for the binary outcome, but also it works very well for continuous outcome. So it ranked consistently high. And so let's start with these data sets. So these are all well-known data sets for people who develop prediction methods. So they're breast cancer data, brain cancer data, prostate, and so on. And one thing to note is that the sample sizes are relatively small. Notice 76 human subjects and so on. But the number of genes was typically very large. So these are genomic data. And when we applied these different prediction methods that I mentioned earlier, we can, of course, report accuracies. And so what do we learn? Let's look at one particular data set, adenocarcinoma. So here, the random GLM has an accuracy of 84%, and these are the accuracies of alternative methods. And the one, I mean, overall, the story is that all methods work fairly well. That's the good news, you know. And but in any event, you can go through this exercise and then estimate the mean accuracy. And what we learn is this random GLM method really ranks highly. You know, it takes the #1 spot. And so that's encouraging. But here's the limitation of this study. Although this is actually the largest empirical study involving gene expression data that I'm aware of, evaluating predictors in 20 data sets is still not enough, you know. And so Lin Song then evaluated these different methods using 700 data sets. And how did she generate so many data sets? So she used a trick. So we started with 7 human and mouse expression data sets. And so we randomly chose one gene and considered it a gene outcome or gene trait. And then we dichotomized that gene expression level by the median. And so suddenly we have a binary outcome. And then we used the other gene expression data to predict this binary outcome. Do you see? It's an artificial way of creating an outcome. But for the purposes of evaluating prediction methods, it's as good as any other, you know. And so here are the box plots that show the prediction accuracy of these different methods. And what we learn is that, yes, this random GLM is slightly better than all competing methods. It works better than the random forest. Actually, it almost ties with the random forest as long as you choose a high value for the parameter of the random forest, which is known as the M-try parameter. Remember, all of these methods have default choices for their parameters, and so we always chose the default values, but for the random forest, there's one result that reports the default choice and one where you increase M-try, and then it almost ties. But it really outperforms other popular methods. For example, computer scientists love support vector machines, and clearly this random GLM is better. The other thing that is of interest here is to compare the random GLM to just a forward regression model. Remember how I told you when you have a logistic model and you apply forward variable selection, it's a terrible thing to do. And the first box plot shows that, right? Comparing the standard forward logistic model versus the random GLM reveals that, yes, the random GLM is better. You know. Oh, yes?
I was just wondering why, based on what you said about forward GLM, overfitting and random forests and generally doing a better job because they bag, why would forward GLM work as well as random forests?
Yeah, it's surprising, I agree. I would have thought forward GLM is much worse, but I guess the message is that when you dichotomize one gene trait, then the remaining genes actually have a lot of information for that gene. I mean, the other thing to look at is the prediction accuracy. It's close to 80%, you know. That is not a complex disease, right? We would love to predict a complex disease based on gene expression data and get an accuracy of 80%. You know. but here the signal is very strong, and therefore all methods perform reasonably well. In any event, one limitation of this analysis is that we use genomic data, few samples, many variables. And in the machine learning community, people have assembled the so-called benchmark data. If you do any research where you propose a novel prediction method, the reviewers will hopefully ask you to evaluate your method on these data sets. And these data sets have relatively few features. Think of it as variables. There are few variables, but hundreds of samples. And let's now evaluate these different methods. And it turns out, when you compare these different methods, the random GLM predictor performs as good as other methods as long as you make one crucial modification, which is you need to allow for interaction terms, okay? And why is that? Going back the slide, notice there are few features. And the random GLM really seems to perform best if you have many variables. And one way to create many variables is to introduce pairwise interactions between variables. You could, of course, ask, what if I introduce three-way interactions? And we tried it. It didn't help. It's here, pairwise interactions was the thing to do. And if you do it, then the random GLM ties with the random forest and also with the support vector machine. So remember how I said support vector machines are very popular methods and very powerful methods. And one reason why they are popular is because they perform very well on the UCI benchmark data. They just perform well. But I'm just saying, certainly other methods tie with that performance. Yeah. All right. We also did a lot of simulation studies to evaluate these methods, and consistently we found that the random GLM works well. Other methods also work well. These are mouse tissue data where, remember, I keep coming back to Jake Lucis's data with physiologic traits, HDL, body mass, insulin, blah, blah, blah. And you can ask, how well can I predict these clinical traits? And here we don't dichotomize them. We use continuous traits, and use a random GLM for a continuous outcome. And again, it works really well on these real data. And also when we use now these 700 gene expression traits where we don't dichotomize the trait, but just leave it as a quantitative trait, and then again, this method performs very well, certainly compared with the random forest. Same in simulations. Now, the one critical comparison is really with penalized regression models. I love penalized regression models. I think many of you have used things like Lasso and ElasticNet and so on. And there's an R package, GLMNet, not developed by our group. I apologize, I forgot who the author is. But in any event, so we then compared the random GLM to the GLMNet predictions. And so we compared it on all of the data that I mentioned, these 20 disease-related expression data, the 700 dichotomized gene traits, UCI benchmark data, and simulations. And here I report the difference in accuracy and between random GLM and ridge regression, first column, ElasticNet, second column, and the Lasso. And we see slight improvements in accuracy. I mean, so underneath the numbers you see p-values. So although they are sometimes statistically significant, they may often be negligible in practice, but in any event, so it works well. Having said this, these penalized regression models have several major advantages. The first is if you apply an approach such as Lasso, you really end up with very few variables, which is attractive. And also, these approaches are much faster to calculate. They can GLM net may take a few seconds, and the random GLM may take a couple of minutes, you know. We did these comparisons both for binary and continuous outcomes, and again, random GLM did compare favorably compared to these penalized methods. Now, I want to come to another topic, which is, let's say you have, yeah, go, please. Yeah.
So oftentimes these methods work well when you in cross-validation, but when you use a true test set, the accuracy is much, much lower.
Yes. So the question is, did we use cross-validation, or the comment is that often when you used cross-validation, you got one set of results, and if you applied it to test set, another one. I didn't mention it here, but here's how we estimated accuracies. We always split the data into 2/3 for the training set and 1/3 for the test data. And then we did this splitting, I want to say, a couple of hundred times and averaged the results.
That's cross-validation. So if you trained a model, say, on Framingham data,
yes,
and then you use that data to predict like risk in Californians,
yes,
it will be very different.
yes. Unfortunately, that's true. So the comment is that sometimes you train a predictor on one training set, for example, Framingham data, and apply it to another cohort study, and the accuracy is terrible. And that plagues all genomic analyses, batch effects, biases, and so on. It's not so much a problem of the prediction method, it's rather a measurement issue, right? You want to ensure that the data are measured in the same fashion. And it also reflects heterogeneity and all sorts of things, you know. But yeah, go ahead.
And since RGLM is also an ensemble approach, how do you get around the interpretability?
I'm so glad you asked. So the question is, given that the random GLM is an ensemble predictor, why do I claim that it's more interpretable, you know? There are several answers to it. The first answer is it actually involves far fewer variables than a random forest, for example. And second, we further reduce the variables using an approach we call ensemble thinning. And at the end of the day, we end up with very, very few variables. Think 10 genes. And then you can use these few genes in one single logistic model if you want to understand what's going on. Do you see? So you have, although you may have started with 500 logistic regression models, you hone in on the most important genes, and you use those in your logistic model, for example, to get an understanding. You know. That's in a nutshell. But on our web page, there's an R software tutorial that describes various ways of interpreting the random GLM. So that was one approach, but there are several others. Yeah. So coming to this topic, how do we arrive at a thinned version of the random GLM? So, and why to do it? Well, the goal is to define a very sparse predictor that involves very few genes. And the idea is very simple. Remember that you have these 500 logistic regression models, for example, and each of them may involve, 3 to 5 genes. But there will be some genes that occur only once, right? They are only present in one of these 500 models. And so then you say, oh, come on, I don't really need that gene. I'll drop it, you know. And I refit the model. And that's the idea, you know. So to give you some numbers, so when you fit a random forest predictor based on these trees, and you look at the variable importance measures, then often it really involves 40 to 60% of the genes you started with. But the random GLM already only uses far fewer genes. And why is that? Remember, it uses forward regression, and that already cuts down tremendously on the number of genes used. So on average, it involves between 2 and 6% of variables. But even that is a lot. If you have 20,000 genes, 2% is a lot of genes. And so, as I mentioned, we now want to thin this predictor further by removing rarely used features. And so we used a threshold with a very long name, time selected by forward regression. Guess what it measures, you know? How the number of times a gene was selected by forward regression in these, let's say, 500 models, you know. And as I said, you can then choose a threshold and you say, I want to remove all genes that were selected 2 times or less, you know. And here I show you some plots how the prediction accuracy, test set prediction accuracy, depends on the thinning threshold, you know. So you notice that when I use a threshold of, let's say, 1 and 2 to remove genes, I barely affect the median accuracy. I mean, it doesn't change much, which is intuitive. Genes that are rarely selected don't matter. Only if you really use a large thinning threshold, you start to get compromises in the accuracy. But on the right panel, I show you the average percent of genes left for the prediction, you know, and it goes drastically down, right? If you have a thinning threshold of 2, 3, 4, 5, you end up with far fewer genes. It has a drastic effect. So, for example, over 80% of features are removed when you use here a thinning threshold, for example, of 20, whereas the median accuracy decreased by 0.009, you know. So what do you the box plot at the bottom shows the number of genes used for the prediction. So after you apply the thinning, notice how few genes you use. I barely can read the numbers, but think like 20, 30, 10, you know. So if you couple, if you employ the thinning approach, you end up with few genes, and then you can use them in a GLM model to predict the outcome, to get a sense of what each gene does, you know. Now, yeah, I will maybe remind you then the random GLM pros and cons. Pros, astonishing accuracy. It often outperforms existing methods. Few features contribute to the prediction, especially if you apply thinning. It's easy to interpret, especially if you apply our software tutorial that shows you how to do it. The thing I didn't mention is it provides these variable importance measures, right? The time selected by forward selection, that's a variable importance measure. And I didn't show a lot of details, but it is a different thing from a t-test statistic. It's another way of ranking genes, for example. Not that I advocate you use it for selecting genes, because I still feel that if you want to learn biology, using intramodular connectivity is a better approach. But in any event, that it is a variable importance measure. The other thing I barely mentioned was that ensemble predictors allow you to estimate so-called out-of-bag, provide you out-of-bag estimates of the accuracy. So these are similar in spirit to a leave one out estimate of the error rate. It's almost an unbiased estimate of the error rate, which is an attractive thing to have. And then Peter Langfelder generalized now our random GLM R function so that it really can deal with all sorts of outcomes: binary, quantitative, count, multiclass, survival. There is one con, which is it is slower than, for example, the elastic net or penalized regression model. It typically doesn't matter when you deal with, I want to say, a few hundred subjects, you know. It depends on certain parameter choices, but I've applied it to predict outcomes based on, let's say, 8,000 human subjects, and then you do notice it, you know. Then it may take 3 hours, you know, or so. So as I mentioned, it's all implemented in an R package called Random GLM, and we have created several tutorials. And so I hope you try it out. You know, that's I think it deserves a look based on the empirical data. And then I remind you, if you have a low-dimensional data set, let's say only 5 biomarkers or 10 biomarkers, then you want to create interaction terms, you know, in order to improve the performance. So, are there any questions at this point? Yes?
So when you get the variables that get selected at the end, when you test for accuracy, do you just add those variables into like a logistic regression model?
Yes.
So the variable importance does not have a role? Like
No, it does play a role, right? So let's, okay, so let's assume we applied our predictor and we find the out-of-bag error rate is high, 90% accuracy. That will be great. We will be enthusiastic. And but then you want to know, well, why is it so high? Which genes were selected? And then by all means, you would want to look at time selected, you know. And you would say, wow, these 3 genes really were selected many times. They contain the main signal. So on that level, you already arrive at an interpretation. But then you could go a step further and say, all right, it really involves multiple genes, and how do they combine to arrive at a prediction? And our function outputs actually all the coefficients. So you get the coefficient values from all 500 logistic regression models, and you could look that up. But what you can do is you can just average the coefficient values across all 500 predictors. That is another way to interpret it. But the third way is to focus on these, let's say, 5 or 10 genes that were repeatedly selected and just put them into a single logistic model. All of these tools allow you to get a sense which genes matter, why do they matter, and so on, you know. It will never be as good as using just forward variable selection, because you end up with one model. But I think I showed you that forward selection is really a bad strategy, you know. I want to mention one very important aspect of the random GLM which makes it attractive. There is an option to force variables into the model. So why would you want to do it? Imagine you have gene expression data for predicting lung disease. And what do you know? Well, smoking matters, age matters. And so you want that these variables are always part of every single logistic regression model. So you want to make these variables mandatory. And so there is an option then in the random GLM function where you say the following variables have to be mandatory. They should be part of every GLM. And that can make all the difference in accuracy. Whereas with other tools, for example, the random forest, there must be a way to do it. I just don't know how to do it in the R code, you know. But in the random forest, by definition, it randomly selects subset of genes, and I just don't know how to enforce mandatory variables in each tree. It doesn't work. And so when we compare the random GLM to the random forest, which is a state-of-the-art method, that's where we get the biggest bang for the buck if we force mandatory covariates into the model. And yeah, so you can analyze methylation data and these mandatory covariates in a combined fashion. Yeah.
That's a really great feature, because
Yeah.
I realize with random forests, sometimes there will be this phenotype variable that you know for sure makes a difference, but if you try and add it with the gene expression, like just as a variable into the model,
Yes.
it won't pick it.
It won't be selected, exactly. And so I agree, this is actually something that works well. I do have if you just Google search random GLM predictor, you'll find a web page. And I know you guys are crazy about R code, so I will give you that, you know. So there's, so here's one, what we call mini tutorial. And so you load it into, I just want to make things larger. So you read the library into your R session, random GLM library. You say, give me this mini data set. And then there's an outcome and variables. And then you see in essence, it's one R command where you input the X are, for example, your gene expression data, Y is your outcome, and optionally you can have a test set. So X are the training data, Y is the training outcome, and here you have the test set data. And one thing you learn from here is that there's a variable called number of threads. And what does that imply? Well, this code is highly parallelizable. Remember how I mentioned it's computationally a bit more intensive. But if you have a multi-core machine, you can say I have 8 threads, and it does help a lot, you know. It's not terrible. If you have a small data set, don't bother. But yeah, and then so you fit this model, and then in order to get the test set prediction, you just again use this $sign and say, give me the test set prediction. And here is how you can. One attractive thing about this predictor is it actually gives you probabilities, right? It would give you the probability that you have the disease, yes or no. And so that's how you get these probabilities. This is how you arrive at the variable importance measure, you know, for ranking the genes. Here I show you the 20 genes that were selected most frequently, you know, it gives you a sense. Here I show you a bar plot of the variable importance. So it says for this Affymetric probes, the importance was as follows. And here I show you how to fit a continuous outcome, you know, for example, HDL levels or any other outcome. So it's the same logic, you know. And with that, any final questions? Okay. So thank you. I think that ends our questions and our lecture. I want to thank you again for staying for such a long time. I think when you go to bed tonight, you will hear this terrible voice in your head, and and I just want you to know it's my voice, you know. So after a few days, it will diminish, you know. But other than that, I think I'm pretty good about responding to emails. Peter Langfelder is even better, so always CC both of us, you know. And have a safe trip home. You know. Thank you.